This is a video for AQA Further Pure Mathematics, Hyperbolic Function, Section 2.2, Differentiating Inverse Hyperbolic Functions. So start off first of all by trying to differentiate sine inverse of x. We're using the -1 notation here, however you could alternatively use r sine x as an alternative. The reason I'm using -1 is that this is the notation that you'll find on your formula sheets. The method is similar to methods you may have seen previously for sine inverse and cos inverse. So we start off by saying that if y is equal to sine inverse of x, then it must be true that sine y is equal to x. And then we can use implicit differentiation to differentiate both sides with respect to x. So the derivative of sine is cosh, so on the left hand side this becomes cosh y, but we must multiply that by the derivative of y dy by dx, and on the right hand side we get the derivative of x, which is 1, and therefore dy by dx is equal to 1 over cosh y. Now we'd like to get this as a function of x, so we can use the identity that cosh squared y minus sine squared y is equal to 1, and therefore cosh y is equal to the square root of 1 plus sine squared. But we know that sine is equal to x, and therefore we can say that this is equal to 1 over plus or minus the square root of 1 plus x squared. So that came from cosh squared y minus sine squared y is equal to 1, and therefore cosh y is equal to the square root of 1 plus sine squared y. But we've got that sine is equal to x, sine y is equal to x, so this is equal to square root of 1 plus x squared, and plus or minus that. However, we also know that the gradient of sine inverse is always positive, so we can take the positive square root and say that the derivative dy by dx is equal to 1 over square root of 1 plus x squared. So we had the standard method of writing if y equals sine inverse x, then sine y must be equal to x, differentiating implicitly, and then using the identity for cosh as being the square root of 1 plus sine squared y. There is an alternative method of doing that, and that is to use the logarithmic expression for sine inverse of x, which is this one here. And you might like to check that this produces the same answer. You have to be a little bit careful using chain rule differentiation, but you should be able to show that you get exactly the same result. The same method can be used to differentiate cosh inverse. So you can see that we have to write cosh y is equal to x, differentiating implicitly again gives dy by dx is 1 over sine y. But this time there's a slight difference because we're looking for an expression for sine y, so therefore that's equal to the square root of cosh squared y minus 1, using the same identity, but this time we want sine y. And therefore dy by dx is 1 over the square root of x squared minus 1. Again, we can take the positive square root because we know that the gradient has to be positive. So we have these two results then. First is that the derivative of sine inverse of x is 1 over root 1 plus x squared, and the derivative of cosh inverse of x is 1 over square root of x squared minus 1. Now you will actually find these in your formulae booklet, however you'll need to look in the integration tables and work backwards from the integrals that you're given. They're not given explicitly in the derivatives table. Once we've got these, they're actually particularly useful to be able to extend the range of functions that we can integrate, and we'll be looking at that in the next video. So an example of how we might use this then, here we're asked to differentiate sine inverse of 4x. We all have found now that the derivative d by dx of sine inverse of x is equal to 1 over the square root of 1 plus x squared. So all we need to do then to work out the derivative of sine to the minus 1 of 4x is to substitute into the formula 4x instead of x. So we'll get 1 over the square root of 1 plus 4x all squared. But you must remember that its chain rule applies, so we must multiply by the derivative of 4x, which is 4. So therefore we end up with 4 over square root of 1 plus 16 x squared. Well, that's the end of this video looking at differentiation of sine inverse and cosh inverse. And in the next video we'll be looking at integration using inverse hyperbolic functions.